Alright, so now we're looking at example 3 on speed control for DC machines. And the problem reads, a 325 volt shunt motor has an armature circuit resistance of 0.25 ohms and a full load speed of 1250 revolutions per minute. The armature current at full load is 55 amps, and then they say to us we need to calculate the resistance required in series with the armature to reduce the speed to 1000 revolutions per minute with full load torque. Alright, so let's look at A first. So what I've done is I've drawn two circuits to show you the circuit at the first speed, at full load speed, and then the circuit at the second speed. So here we have the supply voltage of 325 volts. We have the armature current, which they told us was 55 amps. And we have the armature resistance, which they told us is 0.25 ohms. They didn't tell us anything about the shunt coil, the field coil. They didn't tell us the resistance of it, and they also didn't tell us how much current is flowing through the field winding. Now, remember, with a shunt motor, like we said in the previous video, the voltage of 325 volts is across the armature, and that same voltage is across the field windings. And the field winding isn't changing. We're not changing the resistance of it. We're not changing the number of windings. So therefore, the field current will stay constant. And if the field current stays constant, the flux that this field is generating will also stay constant. Now, on the other side, we have the second scenario for N2 when the motor is running at 1000 revolutions per minute. And to do that, they told us that they had to put a series resistor in series with the armature. So we're going to call that series resistor Rx, and they want us to find out what that is. So what we need to remember is when we are dealing with these DC machines, if we are modifying the armature, it's called armature control, and then we're going to be expecting the speed to slow down. And in this case, we don't have to guess because we can see that the speed was 1250, and when they put the resistor in, the speed slowed down to 1000 revolutions per minute. Okay, so let's see how we solve this problem. So first of all, we go to our formula sheet and we look at this EMF equation for the back EMF of the motor. Right? So here we have it here. So E1, so this is the back EMF over here at E1 equals the voltage times the armature current times the resistance of the armature. And we have all those values. They gave us the full load current, they gave us the armature resistance, and they gave us the voltage. So we calculate the back EMF to be 311.25 volts. All right, now we have that. We want to calculate the back EMF when the motor is slowed down. Okay, and this is the same formula, but you can see I've separated the armature resistance into Rx and Ra. So we know what Ra is. It's 0.25, but we want to know what is that resistor that we've put in there to increase the resistance to slow the motor down. And we have the voltage and we have the current. All right, and we'll get to that now, why we have the current. So first of all, we need to calculate what E2 is. So because we don't have that resistance that we've inserted, Rx, we can't calculate the armature, or sorry, the back EMF of the armature. So we're going to go to this formula on our formula sheet, this one over here, and we're going to use that formula to calculate what E2 is. And if you look at that formula, K is constant for both situations at N1 and N2 because it's the same motor, so the constants we can cancel out. The second thing we can cancel out is the flux 1 and flux 2. Why is that? The reason is, just like we said in the beginning of the video, it's a shunt motor and the resistance of the field winding is not changing, and the voltage of 325 is across the field windings. So flux 1 is equal to flux 2. Okay, so we can cancel those out. Now all we're left with is N1 over N2. And we have those two speeds. So we said it was 1,250 for N1 and 1,000 for N2. And we have the back EMF at 1,250 RPM. And then we can very easily calculate E2. And that's what I've done over here. So there's the formula now. And we substitute the values in. And then we get the new value for E2, which is 249 volts. Now, I always like to point this out. If you look at the back EMF when the motor is at 1,250 RPM, it's 311.25 volts. And if we look at the back EMF when the motor is slowing down, the back EMF is decreased. So that's what we would expect, because the slower the motor goes, the less back EMF the armature generates, because as it slows down, the back EMF starts collapsing. So that's what we would expect, 249 volts. All right, now once we have that, we can go back to this formula on top here, and we can substitute En. So let me move that up a bit. We can substitute E2 into there. We have the voltage. We have the resistance of the armature. We still don't have Rx because that's what we're looking for. But do we have the armature current? And how can we know what that armature current is? And you can see I've written 55 here, which is the same as IA1. Now, how can I say that's true? If you look at the question, it says that the full load current is 55 amps. And then in part A, they say even though the speed is reduced to 1,000 revolutions per minute, the full load torque, it's still, so sorry, let me say that again. Even though the speed of the motor is reduced to 1,000 RPM, the motor still has full load torque. So the torque hasn't changed from this one to this one. So the torque hasn't changed. So therefore, they're telling us that T2 equals T1. And why can I say then that IA1 equals IA2? And it's because of this relationship here. T is proportional to the armature current times the flux. And just to remind you guys again where we got that from, it's from this formula. If we cancel out all the constants, we're going to be left with T equals the flux times the armature current. So it means the armature current is multiplied by the flux. So if you change the armature current, the torque will change. If you change the flux, the torque will change. And because it's a shunt motor, like we said earlier, because it's a shunt motor, the flux is constant. So if the flux is constant here, the torque is constant, the armature current has to also be constant, because if we change this value in any way, the torque would change. So that's how we know. So when T2 equals T1, the flux is constant, therefore the current is also constant through the armature. So there we have IA2 now, which is also 55, and then we can very easily calculate Rx, which we get to 1,132 ohms. Okay, and then let's quickly look at the last part. They say to us the speed at which the motor will run if the load torque is halved. And it says ignore the effects of armature reaction. So now we want to know what the new speed is if the torque is halved. All right, so let's look at that. So now what they tell us, so the torque is halved. So it means T2 equals 0.5 times T1. So what that means, torque 2 is half of what T1 was. Then we go to our formula sheet, and we can use this formula for torque, and we can calculate what the new torque is very easily now, because the K's cancel out, the fluxes cancel out because it's a parallel circuit, or it's a shunt circuit, and we're only left with T1 over T2, IA1 over IA2, and we can substitute in T2 over here, we can substitute 0.5 T1, which means we can cancel out the T1s, and then we have 1 over 0.5 IA1 over IA2, and we have IA1, which is 55, and IA2 is the new current now, because they told us that the torque is being halved. All right, so if you look at this formula, we said the flux is constant, the torque is being halved, so therefore the only way it can remain proportional is if the current drops. All right, so that's how we get that. So there's our new current, and with the new current we can calculate the new back EMF. So I'm not going to go through that because we have the Rx now, we have the armature resistance, we have our new value for I armature 2, the voltage is the same, and there we get our new back EMF. Then to calculate the speed, we are going to go to this formula again, which was on our formula sheet. We can cancel out the K's, we cancel out the fluxes because it's a parallel circuit, a shunt circuit, and then we can calculate the new speed because we use our new E2 and the old E1, and we have the speed for N1, which is 1250, and there our new speed is now 1152.59 revolutions per minute.